Sometimes we have variables, x and y, that there's an exponential relationship. However, it's not a perfect relationship. And so when it's approximate, we're going to use an exponential regression to find a model to fit the data. And so we're going to use techniques that we've done with linear regressions in order to do that. So just to draw a quick idea of this, an exponential model, and I'm going to draw an exponential growth. Exponential growth looks something like that. Actually, I don't like that. It looks something like that, okay? It starts out slow, but then it grows faster and faster as we go on. And so it's possible that we have something that's growing, okay, something like that, but not perfectly. And so we're just going to be finding an exponential curve that fits that the best. A box containing 1,000 coins is shaken, and the coins are emptied onto a table. Only the coins that land heads up are returned to the box, and then the process is repeated. The accompanying table shows the number of trials and the number of coins returned to the box after each trial. So, for example, before we've done anything, we've done no trials. In other words, we haven't emptied the coins out at all. We've got 1,000 coins in the box. After dumping out the coins and taking the ones that land heads up and placing them in the box, there's 610. So 610 landed face up, and that's what's in the box. And then we keep doing that. Now, here's the data that we have. You'll notice we're actually missing this trial 2 here, which is totally fine. We want to write an exponential regression equation for this here. So we're going to go and call these the x values, and these are the y values. And our general exponential form is y equals a times b to the x. Let me point out real quick that we do know that this is exponential decay because our numbers are getting smaller. Okay, and so we are expecting b to be a number between 0 and 1. Okay, we're going to go ahead and do this regression, and we're going to use Desmos to do this. So in the Desmos calculator, we're going to add our numbers from our table into a table in Desmos. So we're going to do plus for adding, and we're going to add a table in. And we're going to go ahead and put our x values, which are, we've got 0, 1, 3, 4, and 6. Okay. And then we've got our y values for each of those. We've got 1,000, 610, 220, 132, and 45. Okay, so we've got some points here. I'm going to go ahead and zoom out so we can kind of see these. So in our window in Desmos, my x's here are ranging from 0 to 6. So I'm going to go from -1 to 7. And for our y values, we range from, 45 up to 1,000. I'm going to go ahead and go from -1 up to 1,050, just so that we can kind of see that. Okay, notice here we've got our points, and they are coming down and looking kind of like an exponential decay. This is exactly what an exponential decay looks like. It drops quickly and then starts to level out. To do our regression in Excel, notice we've got x1 and y1. Now our general form is this y equals a times b to the x. So if I write that, I need to replace y and x with y1 and x1. So y1, and I can't use equals because it's not actually a perfect exponential equation. So I'm going to do the little squiggly line, tilde, and then I got a times b to the x1. And that's going to give me, and notice how close that curve is to those points. It's pretty dang close. Okay, and it tells me right here what a and b are. All right, so I've got 1002.06, 1002.06, and then times, and then for b, I've got, I'll round this to 0.604. 0.604 to the x. Okay. Oh, and sorry, we're round to the nearest 10,000th. I should make sure I'm reading my my instructions. Now, this didn't give me to the 10,000th, so I'm just going to go type A, and it's going to tell me even more decimals. And the 10,000th is 4 decimal places, so 0.0587. So 0.0587 times, and then B is to 4 decimal places 0.6043. 0.60, oh, I forgot what it was, 6043 to the x. Okay, so that's our best exponential regression model for this situation. Now, use the equation to predict how many coins would be returned to the box after the 8th trial. And that just means that x is going to be 8 here. So plugging 8 in, we have 1002.0587 times 0.6043 to the 8. And so I can type that into my calculator. And in Desmos, actually, it's really nice. I know like A and B are already stored. So I can do A times B to the 8, and that will do that for me. And to be accurate, we're talking about number of coins here, and it doesn't make sense to return 17.8 coins to the box. So we want to round this to the nearest whole number. So that'd be about 18, okay? About 18 coins. Now I want to make a comment about best practice for these types of functions. We have an exponential function that we're creating. We know that A represents the initial amount, and we actually know the initial amount as 1,000. So you could, in your exponential regression, instead of doing A right there, you could just type in 1,000 and say, I'm going to force that to be correct. And you'll see that it changes the B a little bit. Okay. Now, depending on that number, it could significantly change this this curve, or it may not. Now, the number that it gave us for A was pretty dang close to 1,000. So for this one, I wouldn't worry too much about forcing it to be 1,000, because that's still a pretty dang good estimate in our problem.